Hi. In this problem, we are going to look at a very interesting inequality problem. So, given positive numbers a, b, c, d, we have to prove that a cube plus b cube plus c cube by a plus b plus c plus there are terms like this now. There are four terms b cube plus c cube plus d cube by b plus c plus d and so on is greater than equal to a square plus b square plus c square plus d square. So, let's think about how we will approach this problem. The first thing that I would like to see here is we can see that all of the terms are symmetrical. Like there are three out of the four terms A, B, C, D in each of them, right? So there is a clear symmetry in the LHS and RHS also is symmetrical, right? So I want to use this symmetry somehow. So if you think about it, can we split this right hand side into four terms such that they are symmetrical and they carry three of these letters A, B, C each. And when we add those four terms, we should get A square plus B square plus C square plus D square. So basically, what I want to ultimately do is to prove that this quantity is greater than one term here. And similarly, each of the corresponding quantities is greater than one term here, right? So one way to do that would be to simply write this as a square plus b square plus c square by 3, and then you can have b square plus c square plus d square by 3 plus c square plus d square plus a square by 3, and finally you can have d square plus a square plus b square by 3. Think about it. If you add up all of these four terms, what will happen? A square appears three times, right? Once in this term, once in this term, and once in this term. So it will add up to a square, right? Because you have a square by 3 three times. So similarly for all the other letters. So technically we can split the RHS into these ways, and that helps us exploit the symmetry of the problem, right? So ultimately all I have to show is that the corresponding term here is bigger than the corresponding term here, right? So the inequality will be proved if I can show that a cube plus b cube plus c cube by a plus b plus c is greater than or equal to a square plus b square plus c square by 3, right? So this is my new question. If I can show this, then the original inequality is done, correct? So let's think about how we'll go about doing this. So now I'll focus on this problem. So let's do it on the next screen. So I'll say a cube plus b cube plus c cube by a plus b plus c is greater than equal to a square plus b square plus c square by 3. Now, in many inequalities books, you might see that they sometimes say without loss of generality, we can assume a plus b plus c equal to 1. At this stage, if you see standard books in inequalities, you might find this statement that we can assume a plus b plus c is equal to 1. So you might be wondering why we can assume that. Because if you assume a plus b plus c is equal to 1, the question becomes a little easier. It becomes a cube plus b cube plus c cube greater than equal to a square plus b square plus c square by 3, right? But this is only after assuming that a plus b plus c can be 1. But we want to understand why that is correct, why we can assume that, right? So suppose we couldn't assume it, right? We couldn't assume that a plus b plus c is 1, right? So suppose we could not assume it, right? So then what we can do, we know that in the problem it was mentioned that a, b, c, d were positive. So we can divide by both sides of this inequality, this original inequality here, by a plus b plus c whole square. So what am I saying? I'm saying this, and I am putting a plus b plus c whole square on both sides, right? So let's see what happens if I do that. I'm putting a 3 into a plus b plus c whole square here, right? So if I do that, the left hand side becomes like this, a cube plus b cube plus c cube by a plus b plus c whole cube which can be written as a by a plus b plus c whole cube plus b by a plus b plus c whole cube plus c by a plus b plus c whole cube, right? Okay, this is the left hand side. And what about the right hand side? The right hand side looks like a by a plus b plus c whole square plus b by a plus b plus c whole square plus c by a plus b plus c whole square whole divided by 3, right? So now actually if we call this x and this y and this z, the inequality is becoming x cube plus y cube plus z cube is greater than equal to x square plus y square plus z square by 3, right? So can you see that the original inequality, which was like this, has been converted to this form, right? How did we get it into this form? By actually dividing by a plus b plus c whole square on both sides and creating new variables x, y, and z, right? These are your normalized variables. And basically, if you can prove that this is true, then that means that the original inequality is also true, right? Because we can replace x with a by a plus b plus c, y with b by a plus b plus c, and z with c by a plus b plus c anytime, right? So basically, what we are saying is that the original inequality is equivalent to this inequality, right? And that is what we achieve by doing a plus b plus c is 1, no? Notice that if I do a plus b plus c is 1, I had gotten this inequality, which is the same thing, only the variable names are different, right? So it is correct to be able to say that you can take a plus b plus c equal to 1 in this case, and you get an equivalent inequality. This inequality is equivalent to this. So if you can prove this, you are done, right? So now our job has been further simplified, and now our job is this: prove that a cube plus b cube plus c cube is greater than equal to a square plus b square plus c square by 3, right? Great. So now what I would do is I will employ the Cauchy-Schwarz inequality to prove this. Proof by Cauchy-Schwarz. So how do I do that? So let's prove a more general case, right? So what I want to show you is the proof of this inequality. Summation of I goes from 1 to n xi power k by n is less than equal to summation of I goes from 1 to n xi power k plus 1. This is what I want to prove for you. Okay, because now if you notice in this, if I put k is equal to 2 and n is equal to 3, if I put k is equal to 2 and n is equal to 3, I would get this left hand side will become x1 square plus x2 square plus x3 square by 3 is less than equal to x1 cube plus x2 cube plus x3 cube. Notice that that is what we want to achieve here, right? That is what we want to prove here. So I want to show you this general inequality, which is true for any n and any k, as long as they are positive, obviously, right? And that I will prove by Cauchy-Schwarz, right? So let's try to see how this will happen. So first of all, I will write the Cauchy-Schwarz inequality. So let's write it here. The inequality can be written in this form: summation of I goes from 1 to n ai bi is less than equal to summation I goes from 1 to n ai square multiplied by to the power half multiplied by summation of I goes from 1 to n bi square to the power half. So basically this is my Cauchy-Schwarz. So this is saying that the dot product will have lesser magnitude than the mod of A and mod of B if you think of A and B as vectors, right? N-dimensional vectors. So I hope you are aware of the inequality before. So we are going to take advantage of this inequality, right? So how do I start this process here? Okay. So what I will say is I will break this xi power k by n. I will break this like this. I is equal to 1 summation xi power k by n is equal to, I will say, summation I goes from 1 to n, and I can write it as xi power k plus 1 by 2 multiplied by xi power k minus 1 by 2 divided by n, right? Can you see that the powers are adding up? The powers k plus 1 by 2 and k minus 1 by 2 will add up and become k, right? So this is the same term as before. We have not done anything. But what I have done basically is separated it out, and this becomes my AI and this becomes my BI. Just like here. In Cauchy-Schwarz here, we need two terms which vary, right? AI and BI. So I'm just separating it out. And I'm going to employ Cauchy-Schwarz now in this next step. So next step will be less than equal to. So we are saying, let's say this is S is equal to this is equal to this. So S is less than equal to, what is it? We'll square it. So summation I goes from 1 to n. This square will be xi power k plus 1, and whole thing is power half multiplied by summation of I goes from 1 to n, and this square would be xi power k minus 1, right? Divided by n square, correct? And this is also power half, right? Also, I forgot to mention one thing. We are going to prove this by induction. So we are going to do it by strong induction. So right now I'm trying to prove this statement, right? I'm trying to prove this statement. Think of this as the inductive step. So what I mean is that we already know that summation of I goes from 1 to n xi power k minus 1 by n is less than equal to summation of I goes from 1 to n xi power k. So if you think of strong induction, in strong induction, we know that we can assume that the statement that we want to prove is already true for lower values, right? If it is already true for all the lower values, then you prove the next step, right? So I'm going to show you the inductive step. I am assuming that this is true. So this is the statement one step below this, right? The power is, instead of k here, the power is k minus 1, and instead of k plus 1 here, the power is k. I'm going to assume that this is true. And using this, I'm going to prove the final step, right? So I'll make some space here. And what I'm saying right now is that we have S is less than this stuff, right? S is less than equal to summation of I goes from 1 to n xi power k plus 1 power half multiplied by summation of I goes from 1 to n xi power k minus 1 by n square and whole to the power half, right? Whole to the power half. This is because we have squared each term and we are doing Cauchy-Schwarz right now, right? Great. So now, using the fact that this is true, the k minus 1 case is already true, I can write basically here, this part I can write, and I can rewrite it as xi summation of I goes from 1 to n, keep 1 by n like this, and xi power k minus 1 by n. So 1 by n can come out of this summation, right? So 1 second, I'll just explain. So I'm saying 1 by n can come out of this summation. So I can rewrite it as 1 by n xi power k minus 1 by n. And the whole thing is under a root, right? And this part I can write, because this now fits this pattern. So this part I can write is less than equal to 1 by n times summation I goes from 1 to n xi power k, right? And the whole thing will be under root, right? Correct. So basically the overall inequality for us will become S is less than equal to, this was untouched right now. So S is less than equal to summation of I goes from 1 to n xi power k plus 1 whole power half, and here I have summation of I goes from 1 to n xi power k by n. I can bring the n inside again, and this is whole to the power half, right? And what was our S expression? The S expression was this, if you recall, right? This was my S. So I'll write that here. Summation I goes from 1 to n xi power k by n is less than equal to summation I goes from 1 to n xi power k plus 1 to the power half multiplied by summation I goes from 1 to n xi power k by n whole to the power half. So can you see that this quantity is exactly same as this quantity? The only difference is that here there is a power half. And these are all positive things. So I can cancel this here and I can bring this here and write power half here, right? So now I have something root is equal to is less than equal to this, right? So I can cancel the powers here and I have gotten the proof. I have gotten that I is equal to 1 to n xi power k by n is less than equal to summation I is equal to 1 to n xi power k plus 1. So this is proving us the inductive step. So assuming this is true, we have shown the next step. So the powers have increased now, k minus 1 to k and k to k plus 1. So we have done the inductive step. So therefore, it is true for all k values, right? So this implies that our original inequality is correct, because for original inequality, I just have to put n is equal to 3 and k is equal to 2. If I put n is equal to 3 and k is equal to 2, I will get basically a cube plus b cube plus c cube is greater than equal to a square plus b square plus c square by 3, right? So if I get this, I have shown earlier that all of our previous steps were equivalent. So if I can prove this, my original inequality is also done. Like, we have used basically Cauchy-Schwarz to prove this general case. What is the general result we have shown? We have shown summation I is equal to 1 to n xi power k by n is less than equal to summation I goes from 1 to n xi power k plus 1. This general result has a special case here, and this is the special case. And this special case solves our original inequality, right? So hopefully you have understood how we have applied Cauchy-Schwarz inequality here. Basically, we did summation ai bi, I goes from 1 to n is less than equal to summation I goes from 1 to n ai square root multiplied by summation I goes from 1 to n bi square root. And we did this, and we did it by induction. We assumed one power less than this was true, and we used the inductive step to show that this step is also true, which proves it for all n, right? So I hope you have understood something from the problem. If you like the content, please subscribe to the channel, share it with your friends in your groups. It will be very good for me if you guys share the videos, because I want more people to be able to see my content. I'll continue to provide free content for you guys. So look forward to the next video, and I'll see you next time.